The example here is from the UCLA Institute for Digital Research and Education. And here the school administrators study the attendance behavior of higher school juniors at 2 schools. So the predictors here are, well, the number of days of absence is the response, and we have here the type of program in which the student is enrolled and the mark in a standardized maths test. So attendance records are available for 314 students. We have the data days absent, and we have the maths score and the program the student is enrolled in. And the program is a 3-level nominal variable indicating the type of program the student is involved in. So here we will define more clearly this program variable as a factor. The levels are 1 to 3, and we give it labels as general, academic, and vocational. Here's the full data. The data is available on LMS. You will see this later on in the lab. And we have an ID here which we define as a factor. Gender is here charactered because we haven't read the thing as a factor. Maths score, date absent, and the program. Here is a plot of the data, days absent versus program. And you can see that the days absent seems to depend on program. In particular, for general, there's a higher absentee rate, and also probably for academic, not so much for vocational over here. Note the commands here. We're going to let us plot here of simply days against programs. And here is some summary statistics. So look at the, again, code here. So with det, you're going to apply to days of absence. We're going to apply the function which is given here, but this will be calculated by program type. So the function here is, we've got the mean and the standard deviation. And the first part gives the format that will be printed in. So the first thing to print is the mean, which is given, will be having this M and SD in brackets. So M indicates mean and SD in brackets will be some deviation. And this is floating point with 2 decimal places for both of those. And you can see the brackets here which indicate that the next thing will be in the brackets. So if you run this code, you'll get here the mean and the standard deviation for each of those programs as far as days absent are concerned. So general is 10.65 on average. Academic is a bit less. And vocational is even less than that. So as we said earlier, vocational seems to have the lowest mean absentee rate, and academic and general a bit higher. You'll find also, by looking at the numbers here, that the variance, or standard deviation at least, is much higher in these two than in this one. So expect there to be some variation here as far as variance goes. And you can see also that the variance here, if you square these numbers, you get the variance is actually much higher compared with the mean, suggesting there is some over-dispersion in the data. So to fit the negative binomial model, we'll require the library or the package MESS, which has the function glm.nb here indicating negative binomial. And you don't have to give it a family because the negative binomial is what's fitted. So here the model fit is essentially the response variable, the covariates on the right hand side, and the data. That's what we require here. Now the output here you can see is given. We've got significant differences between the academic, the programs, and also for the math score. And further, if you look at the negative binomial dispersion parameter, it's bigger than 1. And the one thing you notice here, as we saw earlier in the lectures, is the residual deviance and the degrees of freedom must be about the same. If you look at the ratio of the residual deviance to the degrees of freedom, that should be close to 1. This also gives you some idea of the parameters we saw earlier in the maths part, the theta and the standard error, which we won't bother with too much here. So by looking at this model, we can see straight away that the number of days absent, at least the log of the mean days of absence, will decrease with increasing math score. It's lower for academic compared with the programs types you can see here. We saw earlier we had academic, vocational, and general. So it's lower for academic, and it's also lower for vocational compared with academic. All those coefficients are significant by the Walls test. Now, we didn't fit gender to the model, but gender, as we saw earlier, was declared as a string variable. To fit gender in the model requires it to be converted to a factor first, but in fact, if you try that, you'll find that it will be non-significant. That's something you can try in the lab. So, program, academic, and general here. It's academic here and vocational with reference to general here. You find that the program academic is 0.4 lower than general regarding the expected log count, and the log of the mean for vocational is also going to be lower compared to general. And you can see what's going on here is by an amount of 0.44 and by an amount of 1.28 as far as the expected log counts are concerned. So to determine whether the program itself is significant, we can compare the model with and without program here, and of course this will be the usual stuff we saw earlier, the deviance test. At the moment we see by the Walls test that the program is significant, but if you wish to test it, you can actually fit without the program. We've got an updated model here, M2, and I've got this likelihood ratio test, which is the Annabelle test, as we saw earlier. It gives you both the first model, which was M1 with just maths, M1 with maths and a program, and the second, which is just maths. You find the degrees of freedom differ by 2 because between the two models you had 2 extra variables or 2 extra coefficients to be estimated for the 2 levels of program. The third was reference, and the likelihood test here gives you a very small p-value, because if you look at these two likelihoods, the difference in the likelihoods here is quite large, or 45 odd with 2 degrees of freedom. The p-value is quite small. That indicates this program is a significant predictor of the days absent. Now, if you fit a Poisson model and actually test for the dispersion, so what we've got is the library AER contains this function dispersion test for this model. You can see this dispersion test has a very low p-value. Now the hypothesis here, the null hypothesis, is that the dispersion is actually equal to 1, and the alternative is dispersion is not equal to 1. The p-value is small, so here we'll reject the null hypothesis. It tells you here the sample estimate of dispersion is 6.51. So in this case, we can see clearly the model is over-dispersed. By comparing the models here, for log likelihood of M1 and M3, M1 was the negative binomial model, M3 is the Poisson model. You can see that the log likelihood of M3 is much smaller here, much more negative. Degrees of freedom is 4. And you can see that the test for those two models, M1 with M3, you'll realize that the log likelihood is larger for the model M1, which was the negative binomial model, and so that is the better model in this case. Regarding the interpretation of the model further, we can interpret the model in terms of the actual count here. So we take a look at the expected values of the coefficients. So here the estimates, we can see that as far as the maths program is concerned, it's 0.99 here. So that means as we increase the value of the math score here by 1, we will get here a decrease by a factor of 0.99. In other words, the absenteeism for a 1 mark increase in math score is 99% of what it was before. Program academic compared to program general has 0.64 times the absenteeism, which is lower, and compared to program general, the vocational program has an absenteeism that on average is 0.278 times that of the general. and we also have the confidence interval here. So what I've said here is actually just been repeated here, that for programming academic, we have 0.64 times the incident rate or absenteeism rate compared to the reference group of program general. Vocational is 0.28 times, in other words 28% of the absenteeism for general, and the percent change in incident rate of days absent is 1% decrease for every unit increase in maths, or if you like, it's 99% of the absenteeism for an increasing of score of 1 in maths. So that's by and large what we need to do with this. The important thing here is that you need to be able to fit the negative binomial model where you have overdispersion in the Poisson model. You shouldn't fit this for small sample sizes because the approximation isn't very good in this case. Now, as we saw earlier, you can use the negative binomial to model overdispersed Poisson models, but not underdispersed, because the mathematics tells us that it doesn't take care of the underdispersion. Another common problem we have with models is that we have what's called zero inflated data, where you've got a lot more zeros than you would expect for a Poisson distribution. And actually this is not so much over dispersion as under dispersion, because you've got a lot of zeros in one place, and that will reduce the variance somewhat. Another issue is where you've got no zeros at all, and that may be what we call a zero truncated Poisson distribution. And so that needs to also be modeled separately. Of course, as we saw here, negative binomial regression cannot have negative numbers in it. That's enough for this week. We'll see you in the lectures. Thank you. Bye.